When you kick a ball, you are exerting force on it for a brief time interval, only as long as your foot and the ball are in contact. If we were to graph the force versus time, it would look like this. The force is 0 until the foot touches the ball. It then quickly rises to some maximum value, and then drops back to 0 as the ball starts moving and is no longer in contact with the foot. As you see, there is a well-defined time interval or duration for the force. Only during this time interval, the force has an effect on the ball. A harder kick will make this curve higher, and a kick of longer duration will make this curve broader. Thus, the area below the curve in a force versus time graph is an indication of the effect of the force. We call this quantity linear impulse. As you can imagine, the shape of the curve can be really complex, so calculating the area below may get tricky. A way to estimate the impulse is by considering the average force acting on the ball. If we plot this average force over the same time interval, we get a rectangle. The area of this rectangle is the same as that of the real force curve over the same interval. And so, we can calculate the linear impulse as the product of the average force and the time interval. Note that we have the product of a vector, the force, and a scalar quantity, the time interval. Therefore, the linear impulse is a vector quantity. But since usually the average force is not known, we need calculus to obtain the value of the linear impulse. As you know, integrating a given function over a certain interval of the independent variable, we get the area below the curve that graphically represents that function. Hence, the general expression for the linear impulse is this one. Only for a constant force, by integrating this expression, we get a relation analogous to the one we had for the average force. Let's now do some math with the definition of linear impulse. We know that force equals mass times acceleration. We can thus replace the force in the integral by this relation. We also know that, by definition, acceleration is the derivative of the velocity with respect to time. Integrating, we see that the linear impulse equals the mass multiplied by the change in velocity. Now, the product of the mass and the velocity is called linear momentum. Therefore, the linear impulse of an object is namely the object's change in linear momentum.